In this video, we're going to look at Kepler's three laws of planetary motion. Now, Kepler's laws were derived using observations made by Tycho Brahe. And what Tycho did every night for many years, he and his team went out and they plotted the positions of the planets and the stars in the night sky when they were visible. And of course, they had to do this for many years because they wanted to analyze those motions and understand them. And particularly the planets, because as we talked about, the planets move very differently from how the stars move. And so night after night, year after year, Tycho and his team went out and measured the positions of the planets. And after he died, the data that he had collected made its way to Johannes Kepler, who had worked with Tycho for many years. Now, Kepler was able to take this data and use it to uncover relationships and laws about how the planets move. So in this video, what we want to do is we want to go through Kepler's three laws of planetary motion and try to understand what they're telling us about the physics of how the planets move. His first law tells us that planetary orbits are ellipses with the sun at one focus. Now, in order to explain just how revolutionary that was, let's talk about what an ellipse is. And one way to talk about how an ellipse is how you can draw one. Because an ellipse is not just an oval shape. It's true that all ellipses are oval-shaped, but not all oval-shaped things are ellipses. And so we want to talk about what it is that makes something an ellipse. So in order to understand what an ellipse is, let's first think about how we can actually draw an ellipse. And so one way, the classic way to do it, is to take two thumbtacks and a length of string, and you use the two thumbtacks to lock down the piece of string onto a piece of cardboard or something like that. And then you take a pencil and you catch the string and you pull the string until it's taut. Now you trace around in a circular way and let the string guide you. And this will cause not just an oval shape, but something that is actually an ellipse to form. Now, let's imagine as you're tracing around this elliptical shape that at some point the pencil is going to be right there. In that case, the string is going to go from there to there and there to there because it's tacked down by the thumbtack. And so one of the things that's interesting is that as I trace the string, the length of the string is going to be constant. So from this thumbtack to the pencil, and from the pencil to the other thumbtack, if I add those lengths of string together, I'm going to get some number. And if I choose it when the pencil is over here, and I add this length plus that length, the total length of the string is going to be the same. So the distances, the sum of the distances rather, is going to be the same for every point on the ellipse. And so I could imagine picking a different spot. I could pick a spot there. And I will know that this distance from the thumbtack to the pencil and then from the pencil to the other thumbtack, that the sum of those two red distances is going to be the sum of the two blue distances, which is going to be equal to the length of the string. The length of the string's not allowed to stretch, so it's a taut string, it goes around, and it's maintaining that constant length. The fact that any point on the ellipse that you have, the sum of those two distances is going to be a single number, the length of the string, that is a mathematical relationship. And not all ovals will have that property. That is, you can't just, pick 2 points and tie a string and draw any oval. Only ellipses can be drawn this way. Now, the features of the ellipse that we want to talk about are a couple of different things. First of all, the place where you put the two thumbtacks, those are called the two foci. The two foci, or the two focuses of the ellipse. Now, foci is the real plural, but sometimes people will say focuses to make the plural. But the point is that each focus is a special point for every ellipse. And the planets that orbit our sun, they follow a path that is an elliptical path where the sun is located at one focus. Now, the other focus is just out in empty space somewhere, but the sun represents one focus of the motion of the planet as the planet goes around the sun. Now, here's why this was a revolutionary discovery. Kepler realized that the planets orbit the sun not in circular shapes like Copernicus thought, but in elliptical shapes. And this is really amazing because an ellipse is not just an oval shape, it's a specific mathematical relationship. In other words, Kepler understood and he discovered that you can use mathematics to precisely describe the motions of the planets as they move around the sun. Now, some of you might remember from your high school math classes that if you have a circle, and we'll pretend that that's a circle, you can write down an equation. The equation of a circle is x squared plus y squared equals r squared. Now, if you have an ellipse, you can also write down an equation that describes the x and y positions of the points of the ellipse. And that equation is x squared over a squared plus y squared over b squared is equal to 1, where a and b are just constant numbers. And what a and b do, they like change how much the ellipse is smushed out or how close it is to being a circle. But the point is that this is an equation that describes an ellipse. And the fact that you can write down an equation that describes the motion of the planets, this was a big deal. And remember, everyone assumed that it would be circle because people think that circles are nice and nature likes to be simple. We've talked about that. But this is simple, and it's the way that the universe is. It's not as simple as people had hoped, but it is something that can be understood through mathematics. And so this is Kepler's first law. Again, the planets move around the sun. Their orbits are elliptical paths. They move in ellipses. And the sun exists at one of the two foci or focuses of the ellipse. Now there's one last thing that we want to talk about ellipses because it's going to be important for later. If you have a circle, we know that a circle has a radius, and the radius is the same value all around the circle. So if I sweep out the radius there or there, if I'd really drawn a circle, all of those radii would have the same length. But if I have an ellipse, if I go from the center out, that distance is not going to be the same as that distance or that distance. And so what we do is, in order to characterize the size of an ellipse, we talk about the major axis. And the major axis is the one that goes, it's basically the longest line that you can draw all the way across the ellipse. And so that would be the major axis. Now if you go from the center to the end of one side of the ellipse along the major axis, that's called the semi-major axis. And so the semi-major axis is what we use to characterize the size of the ellipse. So again, it's just from the center to the edge of the ellipse along the longest line which you can draw across the center of the ellipse. It's half of the major axis. You might think of semicircle as half of a circle. The semi-major axis is half of the major axis, which is the longest line that you can draw through the center of an ellipse from one side to the other. And so just remember this term, semi-major axis, and remember that it's basically like a radius, but it's a line that goes from the center along the longest possible line. Okay, there are actually three different laws for Kepler's three laws of motion. The second law is the law that says that an imaginary line connecting the sun to a planet will sweep out equal areas in equal times. That's kind of crazy sounding. What does that mean? So let's imagine that we have a planet that's located right there. And we're going to pick a time interval. Let's say the time interval is a month long. So in 1 month, the planet is going to move from here to here. Now, if we draw an imaginary line from the sun to that planet and follow that line as the planet moves from there to there, that imaginary line is going to sweep out the light blue area here. And so this planet moves from here to here in 1 month, let's say, and it's going to sweep out this much area. Now, what Kepler's second law says is that any point you start on the orbit, if you let it go for the same time interval, in this case a month, it has to sweep out the same area. Now if I pick a point over here, say right there, this line is closer to the sun. So in order to sweep out the same area, it has to go faster when it's closer to the sun, from there to there. So it's that. So going from here to there is the same amount of time as it takes to go from there to there. Because what Kepler's law says is that the planet has to move in such a way that it always sweeps out the same amount of area in the same amount of time. And so if these time intervals are all the same, the area swept out at A, at B, and at C, they all have to be the same amount of area. Now that's still a little abstract. What does that mean? What that means is that as the planets go around the sun, they are speeding up and slowing down. But they're not just speeding up and slowing down in a weird random way. They're speeding up and slowing down in a way that preserves the amount of area that is swept out by that imaginary line. We're talking about area swept out. Well, that's just geometry. These, again, are mathematical relationships. And so using these mathematical relationships, we can understand how the planets are going to speed up and slow down as they move around the sun. This is really big for astronomers because we like understanding things. We don't want to just have things like, oh, the planet's speeding up and slowing down. Why is that happening? Well, it's happening because the way gravity works is that it has to preserve the area of this line that's swept out. And so again, this is Kepler's second law. Equal areas are swept out in equal times. Now we can look at the third law of motion for Kepler. And Kepler's third law says that the period of a planet's orbital motion squared, and so that means its year basically, how long it takes to go around the sun. And so the period or the time it takes to go around the sun is generally represented by a T or a P for period. And so we can say that the period squared is proportional to the cube of the semi-major axis. That's a cubed. So the period squared is proportional to the semi-major axis cubed. So that means if you take the size of an ellipse, remember the semi-major axis, if you draw an ellipse, the major axis is the longest line that you can draw across the whole ellipse, and the semi-major axis is the line from the center along that line out. So that's half the major axis, that's the semi-major axis. If I had a bigger ellipse, the semi-major axis, that's our A, that would be longer. And that means it would take longer for the planet to go around the sun. How much longer? Well, the period would be squared for every cube of the semi-major axis. And so if you don't understand, what that means mathematically, if you don't have a picture of that in your head, that's okay. But the key thing here is that there is, again, a mathematical relationship that describes the motion of the planets. I cannot get across to you how big of a deal this was back in the 1600s, because they didn't know nothing about nothing back then in terms of how the planets moved. And here's Kepler coming and looking at all this data that Tycho Brahe had collected for years and years, and he was able to suss out these mathematical relationships and prove that mathematics can be used to understand nature. That was huge, because nature seemed random until people were able to put math to it. Now, let's look at this big chart of data in the middle of the slide here. What we have is we have the orbital semi-major axis, that's our A value, and it has units of AU, that stands for astronomical units, and we're going to talk about what that is in a minute, but that's just a length, like a mile or a kilometer. It's not a mile or a kilometer, but it's like that. It's just a length unit. And so the orbital semi-major axis A in AU, and different planets, so you can see the Earth's orbital semi-major axis, if I find the Earth, that would be 1.0, and so we'll talk about why it's 1.0 in a minute, but Mercury and Venus are planets which have orbits that are smaller than the orbit of the Earth, and so their orbital semi-major axis is smaller than one, smaller than the Earth's, but the outer planets, which are out beyond the Earth, they have bigger semi-major axis. So what that tells us is that it's going to take longer for these outer planets to go around the sun than it does for the Earth. And so in the second column, we can see how many years, and this is in Earth years, it takes for each of these planets to orbit the sun. So Mars takes about 1.9 Earth years to orbit the sun. Jupiter takes almost 12 years. Saturn takes 29 and a half, basically. Mercury takes about a quarter of a year. So these different planets take different amounts of time to orbit the sun, and that's called their orbital period. Now, this column is talking about something called the eccentricity. That just tells you how smushed out the orbit is. You know, if it's closer to being a circle or closer to being really, really flattened. You don't need to worry about that. It's not really important for what we want to cover. But this last column is really interesting, because if you take p squared, which is proportional to the a cubed, and you have a common set of units, and you divide them, what you end up with is 1. This is 1.002, that's basically 1. 1.001, that's basically 1. Even down here, 0.999, if you round that up, that's basically 1. All of these are basically 1. And so that's a way of understanding distances. Now, one of the things we're going to talk about more is that in astronomy, it's really hard to get a feel for how far away things are. You can't just get a meter stick and go out and measure how far away something is. You have to figure out how to do it based on other information that you know. And so here, we can compare the size of the orbits to the Earth's orbit by simply tracking their motion around the sun and figuring out how long their year is. And so you don't have to get a meter stick out and measure from the sun to Saturn to find out how big Saturn's orbit is. You can just watch Saturn in the night sky and figure out how long it takes to go around the sun. And of course, that's not a simple thing to do, but it is something that is doable. And so once you can figure out how long it takes for the planets to go around the sun, then you can figure out how big their orbit is compared to the Earth's orbit. And that is, again, really a cool thing, because measuring distance is something that's very hard to do in astronomy, and you have to be very, very clever in how you do it. And so this is a clever way that people figured out that they could do it using these mathematical relationships that were discovered by Kepler. So we said that the distance from the sun to the different planets was measured in astronomical units, and we noted that the distance to the Earth was 1. That's because that's how you define the distance of an astronomical unit, which is also called simply an AU. An AU, or an astronomical unit, is the mean distance from the Earth to the sun. And mean means average. It's another way of saying average. So it's just the average distance from the Earth to the sun. Now, if I tell you that the orbit of Jupiter has a semi-major axis that is 11.9 AU long, that just means that it's 11.9 times the size of the Earth's orbit's semi-major axis. And that distance was actually first measured using transits of Mercury and Venus using triangulation. A transit is basically when a planet passes in front of the sun. And so you can actually see a picture here of the sun, and there's this little tiny dot right there. That's actually the planet Mercury passing in front of the sun, which doesn't happen very often, but when it does happen, it's pretty cool. But they were able to use that to measure out how big the orbit to the Earth is, and then they could compare the Earth's orbit to the other planets' orbits very simply using Kepler's law. So that's kind of a cool thing. Of course, now we have more sophisticated ways of measuring distances, and we can actually use radar. So you can see here we have a picture that is showing the orbit of the Earth and the orbit of Venus, and you can imagine that if Earth sends a radar wave out, it's going to bounce off of Venus and then come back and be received. Now, radar moves at the speed of light, and so we know we can send out the waves, and they travel to Venus, and then they bounce back, and it takes a certain amount of time to get to Venus and a certain amount of time to get back. And from that, we know the speed and we know how long it takes for the signal to go there and come back. We can calculate the distance. Now, it's a little bit trickier than that because the Earth is moving and Venus is moving and we have to correct for that. But in principle, the idea is very simple. And so we can actually use radar to measure the distances from the other planets to the Earth very precisely. And that's how we do it using modern technology, which is, again, another very cool thing. But anyway, this is a little bit about how the planets move and how we know how the planets move. And it all goes back down to the discoveries of Kepler and those mathematical relationships that he discovered that explain how the planets move around the sun.